a sounding rocket, a sub-orbital mission is very valuable to demonstrate, to teach, and those sorts of things. Our primary goal is to do science. And so we're here, it's all fun to blast off rockets and see the fire come out and do those sorts of things and worry all the time about them. But the object is to get things into space, to make measurements and do the scientific research. So I'm going to talk about the program and talk about how we're utilized to be able to accomplish that. Next slide. First of all, maybe or maybe not, you have seen a sounding rocket launch. When I was back in high school, I had a friend at school who told me, hey, I saw in the paper there's going to be a rocket launch, a chemical release launch from Wallops, Virginia. And I said, NASA doesn't have a launch range in Virginia. They launch all the rockets from Florida. Well, lo and behold, 40 years later, I actually got a job here as a co-op, and we're launching rockets from Virginia. But we don't only launch them from Virginia. The program is designed to launch them anywhere in the world, and we'll talk about that momentarily. Can everybody hear me? Okay, all right, why don't you just click on that picture. And here's a shot of a Terrier Black Ram 2-stage. Oops. Go back, I want to run that. Click on it. 5, 4, 3, 2, 1, mark. All lanyards straight. Okay, so good smoke. Certainly not the space shuttle launching, but you folks are going to be out there about 1,200 feet from this rocket, and you're going to feel some stuff, and you're going to hear some stuff, and you're going to see that thing blast off. That was a Terrier Black Ram. You're going to fly a Terrier improved Orion, the same booster motor but different upper stage. I watched a space shuttle launch a year or so ago, and you were 3.5 miles away. That's still quite impressive because you can feel the vibrations and the forces from the rocket motor. And if you're any close, you'd probably die. But we can get pretty close here. So we can't do it big, we do it getting close. Up close and personal. Okay, next slide. Now let's look at that same launch from a perspective of a tracking camera. Something you want to try to observe is just as the rocket kind of leaves the launch rail, you'll see some flames shooting out from the sides back towards the back third of the rocket, sort of maybe in the middle-ish. Those are spin motors to get this rocket spinning a little bit quicker to average out misalignments to try to make sure it flies where we want it to fly. Go ahead and click on the picture. It's hard to get help. Just click on it anywhere. There you go. So here we are, left right there. If you caught a glimpse of it, we can always go back and look at it. That Terrier booster motor is actually a Navy surplus asset that burns about 6.5 seconds. And then goes through a coast phase. You can see the rocket spinning. The motor will ignite. And this black ramp motor will burn for about 33 seconds and carry the rest way to its goal. We use this Terrier Black ramp quite a bit at White Sands Missile Range, most of the time there, to carry telescopes and, for looking at the sun and for looking at out in deep space. It goes up to about 350 to 400 kilometers high. Comes down within a 70-mile wide range, and that's why we spin rockets and do the certain things we do. We rely on Newton's laws to get our rocket go where we want it to go. We do very little guidance. At White Sands, we have a system that will guide with canards in the front of the rocket for about the first 18 seconds, but we don't have gimbal nozzles, we don't get fancy. Fancy costs money, and my job is to do this with as little money as possible and launch as many rockets as possible. That's why we try to employ surplus rocket motors, like a Terrier booster, for example. Okay, next slide. Now, one last look, not exactly the same rocket, but it is a view from on board. Maybe you saw some of these videos, maybe she ran some earlier, but we're looking back. Now, this was a 3-stage. You see the white fins in the back. Just in front of the white fins, you see some yellowish things. Those are the 2nd-stage fins, and the black fins are the 3rd stage. We had a problem at Poker Flats, Alaska. The company that built this rocket motor tried to make it better. They ended up messing up the igniter. Even though they did a static firing and a 2-stage firing, they had never flown it in a 3rd-stage configuration. The igniter went off. You could actually see from intensified cameras the flash of the igniter, and the flash of flame coming out the back of the motor, but the motor did not ignite. There was not enough energy and pressure generated by the igniter to ignite the motor at high altitude. So the whole thing came screaming down the 4th-stage, and actually the 4th-stage did ignite eventually on the way down, and it kind of flipped around and didn't do anything, so the mission was a failure. So we went through a couple of years of redesigning the igniter and making some improvements in the motor, and this was a test flight here at Wallops to make sure that motor ignited at altitude before we spent time and money on a payload to go in the field to launch. So, click on the picture. The Talos booster is a surplus motor, right on the sound. Okay. Runs for about 4 or 5 seconds, really quick.
4, 3, 2, 1, 0.
You see the spin motors here firing right there?
Go ahead to the camera.
Now this drag separates, this falls away to your drag. That booster motor is not clamped to the vehicle for compressive loads and acceleration to keep that shaft straight and stiff without breaking the car. For a second stage all the way, that is clamped to the first stage. It moves through a cloud vent here, and we're all waiting for this. Oh, right there. We're all like, okay, at least at night.
Looks good.
Now, because we try to do things as cheaply as possible, we actually integrated an experiment on the payload. With this experiment from Experimenter Guide Space Flight Center to test some room systems out. So here shortly we'll switch to a camera inside the nose cone, looking back. It's on a mast out in front. There's burnout, you can see the exhaust. You'll see it kind of wobbling, so that's called toning. And you'll probably see that right here, the camera inside.
He's done.
Slow down the rocket. So he was testing that mechanism for these booms to make sure they're strong enough and all. And now, of course, we just fly through space about 15 minutes taking data and doing his thing. Some payloads will stop spinning with the telescope. Some plasma physics experiments will continue to spin because you have to just tweak through magnetic field lines to make the measurements. Okay, so I want to make sure you understood what a sounding rocket was before we talk too much more. And I'm not going to read through this, but our mission statement essentially is to deliver payloads to space, suborbital space. Okay, we're not flying at 17,500 miles per hour like the space station has to or the space shuttle. We're only flying about 3,000 miles an hour horizontally at apogee. Our rockets, however, will fly 4 or 5 times higher than the space shuttle flew, but that still does not mean it's going to get into orbit. We still cannot achieve the velocities necessary to get into orbit, so we are suborbital. So again, our job is to carry these experiments, do their thing. We do a lot of development of instruments that eventually go on the satellites. We have done microgravity in the past, and it's a good tool to be able to do that. That's supposed to be done on the space station. However, on the space station, you have fans running, you have life support, you've got the flushing of the toilet, you've got people bouncing around inside there, so you don't get as good microgravity on the space station as you can on the sounding rocket. However, you only get that microgravity for about 10 or 15 minutes, so it's always a trade-off. And so, and one of our things is this is a great tool for training. Education training, that's what you folks are here for, is to take part of that and take advantage of that opportunity. Triple that. Okay, next slide, please. All right, we provide end-to-end support here. We don't build the rocket motors. However, we can design rocket motors. We're working with Marshall Space Flight Center to design a new rocket motor for us. But we do the mission design. We stack and create the vehicles. We'll take surplus motors where motors exist, and we figure out how to make them into a rocket. Fins, interstages, is it stable, is it strong enough, is it stiff enough? We also do the payload development. Every payload is unique. Scientist wants to do certain things. We do have standard subsystems to control recovery, telemetry, but then all the support systems for the experiment itself are always very unique. So every payload is essentially a prototype payload. We do the mission analysis, and we go all over the world to launch these things. We have mobile capabilities, or we can go from existing fixed ranges. Next slide. Of course, we have lots of folks here. We have about 175 contractors who actually do the implementation of the program. I run an office of about 10 people that manage the program and the money and the technologies and to make sure we know where we're going and set things up and establish launch ranges. And then we have the folks that wire and build and construct and technicians and all that. Next slide. The family of rockets we utilize. Again, we try to fit the rocket to the job. We do not fly an expensive Black Grant 12 4-stage vehicle going to 1,500 kilometers to support an educational mission. That's quite a bit of rocket. You still get into space. Of course, maybe you'd love to fly to 1,500 kilometers, but that costs money. So we employ the lower end left-hand side, the Terrier Orion, the third from the left for this mission. However, a lot of our scientists primarily use the Black Grant 9, the Black Grant IX, and then the Black Grant 12, the tallest one. And we've actually taken the Patriot rocket motor. The military had declassified some of the Patriots that we have actually integrated to be a suborbital vehicle for a little bit higher performance over what you guys are flying. So we developed that over the last couple of years. Next slide. Here is that Terrier Patriot. We call it the Terrier Improved Orion, Malamute, because it's still a Patriot missile system, so we don't utilize that name. You're in on the secret. You see the two-stage vehicle here, Terrier booster. That Terrier booster is the same thing you folks use on your Terrier Orion. It's the same booster motor that's used for the Terrier Black Brant. So we try to utilize those motors in various configurations. And there was a liftoff picture of the first flight. We had to fly a second mission to demonstrate that vehicle because we had a roll coupling problem. So the rocket actually was doing a lot of coning between first and second stage ignition. And we had to rectify that by making some changes. And the second flight was very successful. And now we're using that vehicle on RockSat-X, the next step after this rock on. Next slide. Like I said, we go all over the world. Science doesn't occur here in our backyard all the time. It's nice to be able to launch from Wallops as often as possible. It's great for technology missions. It's great for training missions and educational missions. But scientists want to go up to the auroral oval in northern latitudes. So we go to Alaska and Norway. There's a red dot at the very top, which is about 79 degrees in latitude, called Sub-orbital. It's an island up in the Arctic. And you have to carry around your polar bear repellent if you're up there. Does anybody know what polar bear repellent is? It's called a rifle. It's the only thing that's going to be effective against a polar bear. I've not seen a polar bear yet, but when we were up there one time, and I was up there for a couple days, and there was tracks going through the little town / village, research village up there, which was visited by a polar bear that night. So all kinds of extremes. And then there's also the equatorial regions, where the magnetic field is horizontal to the Earth, and so that's of interest to scientists. So we go to Hawaii and to Kwajalein Atoll on the Pacific to do these sorts of things. And the Kwajalein, the only thing to do is to do work and then to snorkel or scuba dive. And so you get to dive with sharks and coral reefs and all kinds of things. So in your off time and doing that sort of stuff. So it's not just a job, it's an adventure. Sort of like the Navy. Next slide. Here's some of these pictures of various sites, anywhere from the tropics, from the equator to the freezing Arctic. Alaska, I had a rocket problem when actually my first rocket I flew for NASA over 20 years ago had a problem. We had to go out and look for it. It was minus 50 degrees. We had to go out in a track to be able to go through the scrub and the frozen tundra for about 5 miles trying to find the thing. So very extreme cold to very hot and humid at Kwajalein Atoll. That middle picture in the bottom with the orange suits. We were at Svalbard, that island to the north. We were taking a little tour with a little motorboat to go around the glaciers, and we had to wear survival suits because we fell in the water. We'd probably be dead in about 30 seconds, so we got to wear these survival suits, but hopefully keep us alive for 60 seconds so they could pull us out of the water. Next slide. White Sands, again, we do a lot of our missions out at White Sands, and here we are on recovery operations. So again, the adventure is flying around the helicopters, going and picking up payloads, and riding back, the doors open, all kinds of fun stuff. Getting stuck on cactus, those sorts of things. It's White Sands Missile Range. There's a lot of exploded ordnance out there. So we're always taught to not pick this up or any little yellow ball or this or that, don't touch, because there could be potentially being exploded ordnance. So again, my job is to keep people from getting hurt, and so we have to be very careful when we do these sorts of things. Next slide. Here's Alaska. You can see a sort of a rollout test to make sure we're getting GPS lock up in the left-hand corner. That's actually in Andoya rocket range in Norway. And then we actually have to cocoon the rockets in Alaska. Now we're in northern latitudes. You know, it's minus 50 degrees, minus 40 degrees. That's cold enough to freeze rubber, and it will crack and fracture. And so we have to keep the entire rocket sort of room temperature. We did have one time a number of years ago that a windstorm came up at night, blew open the bottom of the box down here. And it took a couple hours to get people in to try to fix the box. During that time, the booster motor froze. It cracked.